The notes today are on section 5.3, so we're going to construct functions from a graph, table, list, or description, and these are going to be exponential functions that we're constructing. There's a couple of vocabulary words to get started with. So the first one is in the title. So an exponential function is a function with a variable x, but the x has to be up in the exponent. And so an example of that would be something like this. It's not always going to have parentheses. Sometimes it could have a dot right here, but usually you'll see it with parentheses. But what makes this an exponential function isn't really the number 3 or the number 2. It's this x that's up here in the exponent. So I'm just making a little note there that the x is up in the exponent. And so that that's the placement that makes this be an exponential function. An asymptote is always going to be y equals. For these graphs that we're studying in our class, an asymptote is defined as being a line that the graph gets very close to but never touches. So the exponential functions that we're going to be studying, let's see, this is an example of what one of them might look like. So this is the y-axis, this is the x-axis, and then this black line right here, that's the function. This black line gets really close to this line right here, which in this picture is the line y equals 0. It's the horizontal x-axis. Again, in the functions that we're studying, an asymptote will always be a y equals line because of the types of graphs that these are. You can have vertical asymptotes too, but ours will always be horizontal. If a graph is increasing, as it goes to the right, it goes up. And if a graph is decreasing, as it goes to the right, it goes down. And so these are just two pictures that you can use to help you see the difference between them. And we'll talk about what makes each of these graphs happen as we move along in the notes today. The first example in the notes want us to complete the table for the exponential function. Remember, we're going to do this using fractions, not decimals, for the ones that work out to be smaller than 1. So 2 to the first is 2, 2 to the second is 4. Remember, these numbers are just going in for the exponent right here, that letter x. 2 to the third is 8, and 2 to the fourth is 16. Be careful with these ones. 2 to the third means 2 times 2 times 2, and then 2 to the fourth is 2 times 2 times 2 times 2, so that's where these numbers come from. For this one, any number raised up to the power of 0 equals 1. And then remember what happens over here. When you have a negative number up in the exponent, it makes the value of that expression flip down into the bottom. So this one would be 1/2, that one would be 1/4, this one would be 1/8, and this one would be 1/16. If you type these into your calculators, your calculator can give you the decimal equivalent. And so for these today, I want you to write, see, this one's 0.0625. I want you to write them down. But it's preferred that you give the answers as fractions. I just want you to write down the decimals so you know where the decimals came from too. So part A wants us to draw the graph. A couple of these points are going to be too big to fit on the graph. I'm able to fit all of these ones, all of the really small ones, and then it looks like my graph goes up to, I should probably be able to fit 8 on there. Let's see. I always do the 0 first. So 0 goes with 1, 1 goes with 2, 2 goes with 3, 4, 5, 6, 7, 3 goes with 8. And then over here, -1 goes with 1/2, -2 goes with 1/4, and then these ones you kind of can't even put them exactly in the right spot because they're just getting closer and closer and closer to 0. So you just try your best to make it. The trick though is that they shouldn't look like they're crossing underneath. When I draw exponential functions, I'm pretty bad at it, so I usually do it with pencil, that way just in case I mess up. It should look like a smooth curve, and it should keep going past the end of your graph. And so they both sides should have arrows. This line can't cross down into here. Would you describe the graph as increasing, decreasing, or constant? So as you move across the graph from right to left, they're going up. As you look at the numbers from right to left, they're getting bigger. And so that's how you would decide to describe this graph as being increasing. Remember, the y-intercept of a graph is always the value that goes with where x is 0. The y-intercept is this point right here where it crosses the y-axis. And so on this graph, it's 0, 1. The asymptote of the graph, we set up above that it was always going to be y equals. You want to see where the graph is sitting. So this graph, I'm going to highlight it red. This graph looks like it's sitting right here at the line where x is equal to, or on the x-axis. But remember, this is a horizontal line, and so the asymptote of the graph, it's going to be y equals 0. All of my asymptotes are always going to start with y equals. That's the line that the graph gets closer to, but it never touches. This last part where it asks about end behavior, sometimes students think that this is a little tricky, so I want to make sure that I give you a good description of this part. They want to know as x goes towards positive infinity, which means as x goes to the right and gets bigger, they want to know what's happening to the graph. And then as x goes towards negative infinity, or as the graph goes to the left, what's happening to the graph. So my recommendation for you is that when you're answering questions about end behavior, you're going to put a positive infinity at the top, a 0 in the middle, and a negative infinity at the bottom, and then you're going to do the same thing over here on this side. Positive infinity, 0, and negative infinity. Positive infinity just means it's getting really big, and then negative infinity means it's getting really small. 0 means it's getting closer to 0. So for this one, as x goes to the right, so you're going to trace the graph as it goes to the right. See how the graph looks like it's going up? Out of these three options, it's getting closer and closer and closer to positive infinity. As the graph goes to the right, the numbers are going to keep getting bigger, faster and faster and faster. So positive infinity is the way that it describes that. As x goes to the left, so you're going to trace the graph to the left, x is getting closer and closer and closer to 0. It's never going to, I meant to say y there. Y is getting closer and closer to 0. It's never going to actually equal 0, but it's going to keep getting smaller and smaller, these fractions are. So it's ultimately going to look like it's sitting right here on the x-axis at that line y equals 0, but it's not actually going to equal it. When you fill in these blank spaces, you only have three choices to pick from: positive infinity, 0, or negative infinity. Question number 2 gives me a different function that it wants me to evaluate, so be careful when you type these numbers in. Again, you can use your calculator, but you just want to be careful when it comes to typing them in, because you want to make sure that you get your answers as fractions, not as decimals. Negative exponents make the number flip. Let's see. 1/2 raised up to the first power would stay 1/2. 1/2 raised up to the second power would be 1/4, because remember, you shower the power. 1/2 raised up to the third would be 1/8, and 1/2 raised up to the fourth would be 1/16. And again, you could put the decimal equivalents for these, but fractions are preferred. 1/2 raised up to the power of 0 equals 1, because any number raised up to the power of 0 equals 1. And then for these ones, remember, it's just going to do the same thing that these ones did, but it's going to flip them upside down. So when I put in a -1, it makes the 2 come up to the top, so it'll be 2. When I put in a -2, it makes the 4 come up to the top, that would be 4. So this one would be 8, and this one would be 16. Let's see. On this graph, I'll be able to graph everything besides this first one. I just don't have enough space to graph this one on my graph. Let's see. 0 goes with 1. 1 goes with 1/2, and then a 4th, and then an 1/8, and then a 16th. So it's getting smaller and smaller and smaller. And then on this side, I've got 2, and then 4, 5, 6, 7, and then 8. So you can see how this graph kind of feels like it's doing the same thing. It's just doing it sort of backwards or in a different direction. The graph isn't getting bigger, it's getting smaller as you go from left to right. So as you go from left to right, the graph's going down, the numbers are going down, so you would describe this graph as decreasing since the numbers are going down. The y-intercept is the number that goes with 0, so that's going to be 0, 1 for this graph as well. That's the point right here where it crosses the y-axis. This one, oh, it does ask me for an asymptote, it just does it out of order. So this graph is also sitting on the line where y is equal to 0. Let me color that in a little bit more. I'm trying just to highlight the x-axis. It's not supposed to look like it's underneath at all. So the asymptote for the graph for this one is still going to be the line y equals 0. And then remember, for the end behavior, it's recommended. So positive infinity, 0, negative infinity, positive infinity, 0, and negative infinity. And so when you answer this question, as x gets towards positive infinity, or as the numbers for x get bigger and bigger and bigger and bigger, the graph's getting closer and closer to 0. And then as x approaches negative infinity, the graph's getting bigger and bigger and bigger quicker, so the graph would approach positive infinity for the y's. So that's how you answer questions about end behavior. The next part in today's notes wants us to compare how we know if something is a linear model versus how we know if something is an exponential model. So we know that something is following a linear pattern if it has a pattern of addition, and we know that something is following an exponential model if it has a pattern of multiplication. And so there are going to be different ways that we can answer these questions about which is which. If we're looking at a table versus if we're looking at an equation versus if we're looking at a graph, here I'm going to draw the graphs first. So if something is following a linear model, that means that the graph will be in a line. And it might be going up or it might be going down. That's not what you're trying to decide. But in this one, the graph follows a line. You could find points along that line that have a consistent slope, and so that's what would make a graph be linear. If a graph is exponential, it's going to have one of the different exponential model shapes, and so you can compare them in that way. Let's see. If you were comparing the equations of the points, like let's say I was comparing the equation for this one, it might be something like y equals, I don't know, 2x plus 1 or something like that. Any linear model is going to have an equation that follows a linear pattern. So it's always going to be in that, what did we say this was? Y equals mx plus b. So it's going to be in that format. If we're looking at something that's an exponential model, it's going to be something that maybe looks like this, where you have a variable up in the exponent, and we'll practice that all exponential models are of this format, y equals a times b to the x. That's going to be like the y equals mx plus b equivalent when we're talking about exponential models. The last way that you can compare them is by looking at a table. So let's say for each of these that you have an xy table, and I'll just plug in the numbers 0 to 3. So on this one, if you were comparing them versus on this one, let's see, this would be 1, and then 3, and then 5, and then 7. You could just tell by looking at the tables which one was linear and which one was exponential, because notice on this one, the pattern is that to get from every y to the next y, you add the number 2. But on this one, notice that the pattern is different because it's getting bigger as you go. On this one, you add 2 every time. But on this one, you're not adding 2 every time, you're actually multiplying by 2 every time. So if it's a pattern of adding, it makes it linear, and if it's a pattern of multiplying, then that's what makes it be. In question number 3, it wants us to create a graph based off of a word problem. So on this one, let's see, it says that the number of people attending the event doubles every year. So if it's doubles, that means that the multiplier is going to be times 2. So if in the first year there were 20 people, the next year there were 40. It's not going up by 20. It's important that you notice right here, based on the description, it said it was doubling. So that means that to find each of these subsequent, oh, that's a multiplication symbol. Let me try harder on that one. To find each of the subsequent numbers on the table, you would need to continue that same pattern. There we go, that's a little bit better, of multiplication. So that means that for this one there would be 80, and then for the next one there would be 160, and from this one there would be 320. When you create the graph for this one, let's see, 1 goes with 20, they're counting by 20s over here, 2 goes with 40, 3 goes with 80, 4 goes with 160, and then 5 goes with, oh, it's all the way up here, 320. And so when I draw this, remember I usually draw it with a pencil just in case I do that and mess up, it makes it easier to erase it. For this one, when you draw the curve that goes through it, it should start at 0, 0, and then on this end it can keep increasing. And again, it should look like a nice smooth curve, even though mine's a little bit wiggly here in the middle. They want us to answer questions about end behavior too. So here's positive infinity and 0, here's positive infinity, and here's 0. This graph doesn't cross into the negative numbers, so we don't have to worry about negative infinity. So as x approaches positive infinity, or as x goes to the right, the graph's getting bigger and bigger and bigger. and as x approaches negative infinity, or as the graph goes to the left, the graph's getting closer and closer to 0. For this problem, we are not being asked to create the we're not being asked to create the equation for this one, so we don't have to worry about coming up with a y equals, but that is something that we'll be practicing later. For today, though, we were just practicing coming up with the numbers, coming up with the graph, and then let's underneath right here just write down the word exponential. Because based off of what we practiced with the tables up above, this would be an exponential graph because it's increasing by a pattern of addition. And you can, a pattern of multiplication. You can tell that from the table right here, and you can also tell that from the picture of the graph. So on this example, they want me to practice deciding whether each equation is exponential. So remember, for it to be exponential, based on the definition of how we defined an exponential function, it means that there needs to be a variable up in the exponent. Not just that it has an exponent, but that it has a variable up in the exponent. So we'll go through one by one and decide for these. This one has an x, but it's not up in the exponent. It does have an exponent of 3, but this would be a cubic function because this is raised up to the 3rd power, so that's not an exponential function. This one's a yes because it has an x up in the exponent. This one, the x is regular sized, it's not up in the exponent. This one would be a yes because the x is in the exponent. This one would be a no because the x is not up in the exponent. And then this one would be a yes because the x is up in the exponent. So for the 3 that were yeses, I'm going to circle the x, or whatever variable it is, being up in the exponent. That makes each of those questions be a yes, and then the rest of them are no's. So the last example for this one, it says it assumes that it's an exponential function and it wants you to find the rule from the points. So our goal in this is to be able to write the equation, so the y equals or f of x, or whichever way you're trying to write it. The first thing it wants us to do is find the common ratio. So there's a couple different ways that you can do this. I like to, let's see which way is it going to fit better. I'll do it this way. When I'm doing this, I actually like to make a little table. So let's see, definitely don't need all of these. 3 goes with 12 and 4 goes with 24. And so the first thing I need to do is figure out the ratio. So if 3 goes with 12 and if 4 goes with 24, remember the common ratio is, common ratio is what you're multiplying by each time. So to turn a 12 into a 24, I'm multiplying by 2. And so that means that my common ratio, or the multiplying value, is the number 2. I actually do this one a little bit different. You can plug one point into the equation to solve for a, but I do the work for this second part right here a little bit different. These two were the ones that were given to us from the start. So the 312 came from right here, and then the 424 came from right here. But if you know that you're supposed to multiply by 2 to get each subsequent number, you can go back in time. I mean, not literally, but you could divide by 2 to figure out each of these boxes. Remember, if you're multiplying by 2 to get ahead, then you can divide by 2 to get back. So that would mean that this one would be a 6, and then this one would be a 3, and then last but not least, this one would be either 3 over 2, or you could write it as 1.5. Because again, to get from here to here, you would divide by 2, and to get from here to here, you would divide by 2. Now the reason why I'm doing this and going backwards is because in order to write an exponential function, I need to know two things. I need to know the a value, and I need to know the b value. All exponential functions can be written in this format. You could write a y instead if you wanted to. And then instead of a times b to the x, remember sometimes you'll see it written like this with the b inside parentheses, and that's how I usually write it. So to write an exponential function, you have to know the a value and you have to know the b value. The b value is the number that you multiply by each time. And so for this one, it's the number 2, because that's what you're multiplying by each time. Sometimes it's called the common ratio. It's the number you multiply by to get each next number in the list. The a value is the starting value, and it's also the number that's given to you with the number 0. So I went backwards in my chart enough to figure out what my a value was. So 1.5 is the start, or you could also think about it as the number with 0. So it's the number for y that goes with 0. Once you know those two things, then you're finished and you can write the answer to the question. The a term goes out front and then the b term goes on the inside. And this is the answer to the question. So this means that this graph would start at 1.5. That would be the a value. That's where it would cross the y-axis, and then it would go up times 2 every time to get each of the different numbers in the list. So I can use that same pattern of making the table to help me solve each of these two questions here. Because of the way these problems are given to me, I'm going to do the tables vertically, but just keep in mind that it's the same thing. I'll need to save a space for 0 and a space for 1, and then they gave me the numbers for 2 and for 3. So 2 goes with 100 and 3 goes with 1,000. So to figure out the b value, to make 100 turn into a 1,000, I would have to times it by 10. So that's going to be my b value. You can even put a little b over here if you want to for that one. To figure out the a value, I have to go backwards and I have to figure out what number would go with 0. So if I'm timesing by 10 to turn a 100 into a 1,000, then to work backwards I would have to divide by 10, and then to work backwards again. So to get to here I divide by 10, and then to get to here I divide by 10. And so this one right here, I'll squeeze in a little a equals. That's going to be my a value. My exponential function for this one, you could put the 1 out front if you wanted to, and then the 10 inside the parentheses, or the other way that you could write the answer to the question would just be 10 to the x like this. And since you don't really have to write the 1 in front, you wouldn't need to put the 10 inside parentheses. The directions to this question did say to write them as f of x, and we're writing our answers as y, but just know that those are they're the same as each other. F of x and y mean the same thing. Okay, be careful on this one, because this one starts with -2. And so -2 goes with 4, -1 goes with 8. And so for this one, you're just going to have to leave one empty spot, because remember, you have to make the table go until you get to the number 0. Always start with the smallest number that you're given and try to turn it into the biggest number, for your x's I mean. So to turn a 4 into an 8, I'm going to multiply by 2, so that means that my b value is going to be 2 on this one. And then to figure out my a value, I would just have to multiply by 2 again, and so that would give me the starting value, because again, I would just continue that pattern of multiplication. So for this one, I didn't really leave myself enough room, a equals 16. And then when I write my equation, you can do y or f of x. Remember, both ways would be fine. And so it starts at 16, and then every time it would multiply by 2 to get the next number. 16 isn't truly the number that it started at. I know I said start, but this number that goes out front, remember, it's always the number that goes with 0. So this would be the format of that exponential function.